Welcome to 15-Minute Discourse. Today, we're going to be diving into zero-point energy. It's one of those things, sounds like it's straight out of science fiction.
It really does.
Like almost too good to be true. But we've got all sorts of stuff to look at today. We've got academic papers, we've got patent applications, and even some historical accounts.
Yeah, what's really cool is we're going to see if this is just theoretical or if this could be like the future of energy.
All right, so let's start with the basics.
Okay.
Zero-point energy.
Okay, so imagine any system and you cool it down to the absolute coldest temperature possible, absolute zero.
Okay.
Now, you would think that all motion would stop, right?
Yeah, I would think so.
But the quantum world, it plays by different rules.
Okay, so there's still some energy there, even at absolute zero.
Yeah, exactly.
Okay.
That remaining energy, the energy that exists even in a vacuum, that's zero-point energy.
Okay.
And it's a direct result of Heisenberg's Uncertainty Principle.
Yeah, the one where you can't know the position, A, the momentum.
Exactly. And because of this inherent uncertainty, particles are always kind of jittering around, even in a vacuum, possessing this minimum amount of energy.
So how does this jittering energy, this zero-point energy, how does it show itself? We can't see it, right?
Well, you can't see it directly, but you can see its effects.
Okay.
So, for example, there's something called the Lamb shift. It's a very small change in the energy levels of atoms, and it can only be explained if zero-point energy actually exists.
Huh.
It's like if zero-point energy didn't exist, the colors that we see would all be a little bit different.
Wow, that's wild. It's like this invisible energy field is kind of just like subtly influencing everything.
Yeah, it is.
Wow.
And another example is spontaneous emission, where an atom just suddenly releases a photon, a particle of light, with no trigger.
Huh.
And this can only be explained by this constant interaction with the zero-point field.
Okay, so we have this vast energy source all around us, but can we actually use it?
That is the million-dollar question that scientists and inventors have been trying to figure out for decades.
And it's a tricky one, right?
It's not easy.
I was looking at these research papers, and one of the things that comes up is like the scale of it. The energy density is supposed to be enormous.
It is. Calculations show that it is absolutely enormous. But if it's so enormous, then why don't we see more obvious effects?
Right, yeah.
This is a big mystery, and it's called the cosmological constant problem.
So it's like we're swimming in this ocean of energy, but we can't get a drop to drink.
Exactly.
Okay, and then on top of that, there are issues even within quantum electrodynamics itself, right?
There are a lot of calculations just subtract the zero-point energy. They use a technique called renormalization.
Okay.
It's a way to handle infinities that pop up in the math.
Okay.
But it also makes extracting this energy very problematic.
So theoretically, it's kind of a mess, but that hasn't stopped people from trying, right?
Yeah.
I mean, we have Nikola Tesla, the legendary inventor, and, he was very interested in harnessing energy from space.
He was a visionary. He really believed in the possibility of tapping into these unseen energy sources, and he even proposed devices like the Tesla coil and the magnifying transmitter as potential tools.
But those weren't directly related to zero-point energy, were they?
Well, it's still up for debate.
Okay, interesting.
But moving on from Tesla, let's look at the Casimir Effect, because that seems to be a big focus in the research.
Can you remind me what that is again?
So imagine you have two perfectly smooth metal plates, and they're in a vacuum very close to each other.
Okay.
Now, you would think they'd just sit there, but because of the nature of this zero-point field, they actually get pushed together. It's a force.
So the vacuum itself is pushing the plates together.
Exactly.
That's so weird.
It is, and it's been experimentally proven, so it proves that zero-point energy is real.
Wow, okay.
So now the question is, can we use this force to do work? Can we modulate this force? Can we make it stronger or weaker? Can we create some sort of Casimir engine?
I'm already picturing little Casimir-powered robots running around.
We'll hold on to that thought for a minute. First, let's dig into some of these potential technologies and how they aim to do just that.
Okay.
One of the ideas is to manipulate atoms within these Casimir cavities.
So you take those metal plates, you put an atom inside, and then what?
Well, the idea is that by trapping the atom, you can change its ground state energy level, and you could release some energy.
Okay, I think I need a little refresher on what ground state energy level is.
Okay, so imagine a ball at the bottom of a hill.
Okay.
That ball is at its lowest energy state, its ground state.
Got it.
So by changing the shape of the hill, in this case the shape of the cavity, we can maybe nudge the ball or the atom to a lower energy level and release energy as we do it.
So we're manipulating atoms to squeeze out energy.
Yeah, basically.
That sounds really complicated.
It is. But there are researchers who think it's possible, and our sources even give an example. They say if you inject a hydrogen atom into a Casimir cavity, you could potentially get a measurable amount of energy.
Really? So we're talking about real, tangible amounts of energy here.
Potentially, yeah, but there are some problems because there are these two different theories at play.
Okay.
One is called stochastic electrodynamics. It's like a classical way to explain it.
Okay.
And then there's QED, which is the more widely accepted quantum theory.
Uh-huh.
And they kind of disagree on how this energy release would actually work.
Okay, so maybe not the most promising approach.
It's still early.
What about this microsphere energy collector that I'm seeing here in this patent application? This one sounds pretty sci-fi.
This one is really cool. So this was developed by a guy named Mead, and he was thinking about using tiny spheres to collect zero-point energy.
So instead of plates, now we've got these tiny spheres. What do they do?
Well, the idea is that they have special properties, they have a specific material and structure, and they can interact with these vacuum fluctuations and channel the energy.
So they're like little antennas for zero-point energy.
Yeah. He based all of this on Mie scattering theory, which basically describes how light interacts with particles.
So there's a real theoretical basis for this.
There is, but again, there are a lot of questions about whether it would actually work, and if it did, how efficient would it be? Would we even get enough energy to make it worthwhile?
Right. So maybe not quite ready for prime time, but still interesting.
Yeah, definitely.
So what about this patent I'm looking at for a Casimir force electricity generator? What's that all about?
This one is really interesting because it uses these vibrating membranes inside a cavity, and they would generate electricity directly from the Casimir force.
So it's like a tiny engine powered by the vacuum itself.
Exactly.
Wow.
And what's really interesting is that it kind of lines up with other research on generating photons using vibrations.
So you could turn zero-point energy directly into light.
Potentially, yeah. But again, more research is needed.
Okay, so a lot of promising ideas, but still a lot of unknowns. Okay, well, my brain is officially starting to melt. We've covered a lot of ground here.
We have.
And it's really complex, but it's also incredibly exciting. We've gone from the basic ideas to some really out there potential technologies. But I want to go back to this idea of manipulating the Casimir effect
Okay.
to extract energy. How would we actually do that?
Well, there's a lot of research going on right now looking at using vibrating plates or membranes to kind of modulate the Casimir force.
So like those two plates we talked about, they
Okay.
push together.
Yeah, so imagine if we could make those plates vibrate at just the right frequency.
Okay.
Researchers think that we might be able to create this kind of ratchet effect, actually pull energy out of these vacuum fluctuations.
So instead of just letting them get pushed together, we're making them vibrate and then siphoning off some of that energy.
You got it. It's like we're building a tiny little power plant,
That's a great analogy.
powered by the quantum vacuum.
But it sounds incredibly difficult to actually do.
Oh, it is. The engineering challenges are immense. I mean, controlling those vibrations at such a tiny scale and with the precision needed to extract energy is, well, it's a huge task.
Yeah, I can imagine.
But that's not the only approach people are looking into.
What else is there?
Another interesting area is looking at the materials used for the Casimir plates.
Okay.
So remember the microsphere energy collector we talked about earlier?
Yeah.
The idea there is that if we use materials with very specific electromagnetic properties, we might be able to change how strong the Casimir force is.
Oh, interesting.
We might be able to control it better.
So instead of just using any metal, we're looking for something special that can really interact with that vacuum.
Exactly. It's like we're trying to find the perfect lure for the zero-point energy.
Yeah, I like that. The perfect lure.
But this brings us back to a really fundamental question that we touched on earlier. What is the quantum vacuum, really?
Yeah.
Is it this endless sea of energy, or is it something else entirely?
Yeah, that's a great question.
And how we answer that question has huge implications for whether we can actually extract energy from it.
Okay, so what are the different ways of looking at it?
So one way to think about it is that the vacuum is what's called a plenum.
Okay.
It's just filled with this incredibly dense energy field. And if that's true, the challenge is figuring out how to tap into it.
Right, like how do we get a cup of water out of this ocean?
Exactly. But then there's another way to think about it.
Okay.
Maybe the vacuum is more of a mathematical idea, a way to describe the ground state of quantum fields.
Okay.
And if that's true, then zero-point energy might be much harder to get to.
So maybe it's not an ocean. Maybe it's more like a desert.
Yeah, or a rock. You can try to squeeze water out of it, but you're not going to get very far.
Right.
So on one hand, we have this incredible possibility of limitless energy.
Right.
And on the other hand, we have this very real possibility that it might just be beyond our reach.
Yeah, that's kind of frustrating, but also exciting at the same time.
It is. It's the nature of science, you know? We're always pushing the boundaries, and sometimes the answers are harder to find than we thought they would be.
But even with all this uncertainty, there are people out there trying to build devices that claim to harness zero-point energy.
Oh, yeah. There are definitely people out there who believe they've figured it out.
What are some examples?
Well, there's this patent for something called a ground state energy reduction device.
Okay.
And it involves manipulating atoms in these tiny cavities, kind of like what we were talking about before.
Like squeezing a spring and then letting it go.
Exactly. So this patent proposes using these very specific cavities
Okay.
with particular materials and shapes to kind of maximize that energy release.
It sounds impressive, but is it real? Can we really build something that can do that?
Well, that's where a healthy dose of skepticism is always a good idea.
Yeah.
The theory behind it is based on quantum mechanics,
Right.
but actually building it is a whole other story.
So it's not as easy as just making a tiny box and putting some atoms in it?
Not quite. There are a lot of engineering challenges to overcome, and there could be all sorts of unforeseen problems.
Okay, so maybe not a silver bullet just yet.
Not yet, but it's definitely an area to watch.
What about that microsphere energy collector patent we talked about earlier?
Oh, yeah, that one's really cool.
What was it again?
So the idea is that you have these tiny spheres,
Right.
and they're all arranged in a very specific way, and they act like an antenna for zero-point energy.
Okay.
They capture the energy from the vacuum and convert it into something we can use.
Like a solar panel for the quantum realm? That's awesome.
But again, the big question is whether it's actually possible to do.
Right, because you need the right materials and the right arrangement.
Okay.
And who knows if we can actually figure that out?
Yeah, it's a big challenge.
Okay, so we've got all these really interesting ideas, but it seems like there's still a lot of work to be done.
There is, but that's part of the fun of it, right?
Yeah, definitely. But we also have to be careful because there are a lot of scams out there too.
Oh, yeah, the free energy scams, that's a whole other can of worms.
People are always looking for a way to get something for nothing.
Exactly. And the allure of limitless energy is a powerful one. And unfortunately, there are people out there who exploit that.
So how do we tell the difference between real research and these bogus claims?
Well, it takes some critical thinking, and it helps to have a basic understanding of science.
Okay.
Real scientists, they publish their findings in peer-reviewed journals.
Right.
Their work is scrutinized by other experts. They're transparent about their methods and their results, and they acknowledge the limitations of their research.
So transparency and scrutiny are key.
Exactly. Scammers, on the other hand, they often operate in secret.
Makes sense.
They make big claims without any real evidence to back them up.
So if it sounds too good to be true, it probably is.
Exactly. Always be skeptical.
Okay, so we've talked about the potential ways to harness zero-point energy, the different ways to think about the quantum vacuum and how to spot a scam.
Mm-hmm.
But what about the potential applications? I mean, what could this mean for the world if we could actually make it work?
Oh, that's the really exciting part.
Yeah.
Imagine a world where we don't have to rely on fossil fuels anymore.
Yeah.
A world where clean, abundant energy is available to everyone.
It sounds amazing.
It would revolutionize everything. Transportation, manufacturing, space exploration. We could power our homes and cities. We could send spacecraft to the stars. We could do things we haven't even thought of yet.
Wow, it's like unlocking a whole new era for humanity.
It is, but we have to be careful.
Oh yeah, I was just thinking there could be some downsides too, right?
Yeah, definitely. Any new technology, especially one this powerful, has the potential to be misused. It could disrupt global power dynamics. It could lead to new conflicts. So we have to think about the ethical implications as well.
So it's not just about the science, it's about how we use it.
Exactly. We need to be responsible.
Okay, so a lot to think about, both the good and the bad.
Definitely.
We've covered a lot of ground in this part of our deep dive, looking at the potential mechanisms for harnessing zero-point energy, the theoretical ideas about the quantum vacuum, and even the ethical considerations.
We have.
But there's still more to explore, so join us for the final part of this deep dive, where we'll delve into the history of zero-point energy, the controversies, the ongoing research, and what the future might hold for this elusive energy source. Welcome back to 15-Minute Discourse. We're on the final part of our deep dive into zero-point energy. We've talked about the theory, we've talked about the technology, even the ethical stuff. But let's go back in time a bit. This has always been kind of a controversial topic, right?
Oh, absolutely. It really has. You look back through history and there are all these big claims and arguments, and some people even say that research has been suppressed. It's a big deal, this idea that you could get all this energy from nothing. It goes against a lot of what we think we know about science.
It's almost like that idea of perpetual motion, right? Which we know is impossible.
Right. I mean, the laws of thermodynamics are pretty clear. The first law says you can't create energy out of thin air, you can only change its form.
Right.
And the second law talks about entropy, which means that energy tends to spread out and become less useful over time.
Yeah. It's like everything's running down.
Exactly. So
Yeah.
anyone who says they've invented something that makes more energy than it uses, they have a lot of explaining to do.
Yeah, they got to convince a lot of people.
For sure, they have to show that it works, and they have to explain it in a way that doesn't break physics.
But even with all that skepticism, there have been a lot of smart people who really believed in zero-point energy.
Oh, yeah.
Like Nikola Tesla, for example. He was a genius. He invented AC electricity, and he thought you could get energy from space. Right.
He did. He thought you could tap into what he called the ether.
Right, which isn't really a thing anymore.
No, not really. But even though that idea is gone, his ideas about wireless power and getting energy from these unseen sources, they still resonate with researchers today. And then, after Tesla, you start to see more concrete claims about zero-point energy devices in the 20th century. Like Robert Forward, he was a physicist who looked into using the Casimir effect for energy.
Wasn't he the one with the idea about those charged parking ramps?
Yes. He imagined these ramps that would get pulled together by the Casimir force. But when he did the math, he realized that you couldn't actually get more energy out than you put in,
Oh, so it was kind of a wash.
basically.
What about Harold Puthoff? I've heard that name a lot in connection with zero-point energy.
Oh, yeah. He's done a lot of work on this, even looking into using it for spaceships.
Really?
Yeah, he thought that inertia, the thing that makes it hard to get a moving object to stop,
Mm-hmm.
he thought that might be caused by interactions with the zero-point field.
Wow.
So if you could control that field, you could control inertia, and that could lead to new ways to fly through space.
So we're talking about surfing the quantum vacuum instead of using rockets.
Exactly. But again, this is all very theoretical. There's no proof that it would actually work.
Okay, so it sounds like even though a lot of people are excited about zero-point energy, mainstream science is still pretty skeptical.
Yeah, that's fair to say, but there's still a lot of research going on.
Where are they focusing their efforts these days?
Well, one area is looking at new materials that might create stronger or more controllable Casimir effects.
Oh, like those metamaterials we talked about.
Exactly. Those are materials that are engineered to have special properties. And they can interact with light and other electromagnetic radiation in really interesting ways.
Could they actually be used for zero-point energy?
Maybe the idea is that you could design them to create stronger Casimir forces,
Okay,
and that would make it easier to harness that energy.
makes sense. What else are they looking at?
Well, some researchers are studying vacuum fluctuations in really extreme environments,
Right.
like near black holes, or even in the very early universe.
Wow, that's intense.
Yeah, the idea is that in those extreme conditions, these quantum effects might be amplified.
Okay,
So it might be easier to see them and maybe even control them.
so it's like using the whole universe as a lab.
Yeah, kind of.
And some researchers are even looking at connections between zero-point energy and other mysteries, like dark energy.
It's all connected, it's like this giant cosmic puzzle.
It really is.
But even if we never figure out how to use zero-point energy for power, just trying to understand it has been really valuable. It's made us rethink the fundamental laws of physics, and it's made us question what reality really is.
Yeah, that's pretty deep.
It is, and it shows how powerful human curiosity can be. We're always pushing the boundaries of knowledge, always trying to understand more.
Well, I think that's a great place to wrap things up. It's clear that we've only just scratched the surface of this incredible field. Zero-point energy is complex, it's mysterious, and it's definitely controversial. But it's also incredibly fascinating, and who knows what the future holds. Maybe one day we'll be able to tap into this vast energy source and power our world in ways we can't even imagine right now. But even if we don't, the journey of exploration has been worth it. This has been 15-Minute Discourse. We hope you enjoyed this deep dive into zero-point energy. If you like the show, don't forget to like and subscribe for more explorations of fascinating topics.